So when you add vectors, the answer is the resultant vector, okay? But when you take a vector and you break it into its horizontal and vertical components called resolving vectors, is that yes? Is that good with you? Now, I'm going to try to show you today why that's important. Why is it important to be able to do that? Can you take a look at this vector here and this vector here? They're the same size, aren't they? But what happens when I start tilting that vector at a higher angle? What happens when this angle becomes a greater angle? What happens to this component? What happens to that component? It gets bigger, doesn't it? And what happens to this component? Are you with me or not? Does that make sense to you? That as this angle gets higher and higher, this component starts shrinking and this component starts getting bigger. Is that what you noticed when you did this? So the author wanted you to figure that out. That, you know, as you change the angle, what if I had a vector like that? What's the horizontal component? 0, isn't it? The horizontal component is 0. What if I had just not quite 90 degrees like that? The horizontal component would be really tiny, wouldn't it? All right, I'm looking at your half your faces. Is everybody okay on that page? Okay, let's go to the next one. Now, this chapter has a lot to do with projectile motion, right? Well, here's a projectile, and here's your parabolic path. There's your parabola. And if I were actually sitting on the ball and I had a speedometer on it, and I said, ready, when it leaves the person's hand, oh, what speed are you going? 30 meters per second. As soon as it leaves my hand, 30 meters per second. Well, if I want to try to figure out what's going on here, I'm going to resolve this into its horizontal and vertical component. Now, I'm trying to think, were you okay on this? Were you able to draw the triangles? All right, now let's talk about the physics of it. What was this number here? I'm sorry, this is 30, right? This is 30 meters per second. What is this one? Why? Why is it 20? And you said, wait a minute, I've had that in another chapter. And this is 10, and then it's 0. The vertical becomes 0. What do you call that? What is that called?
Negative acceleration.
Say it?
Negative acceleration.
And it's constant, isn't it? The Earth, little g, gives constant acceleration, right? And because you're going away from the Earth, you could call it negative acceleration. I like that. But isn't it constant? And what does the Earth gravity do? If you go away from the Earth, I will take away 10 meters per second every what? And that's vertically, isn't it? The Earth doesn't know how to take away speed this way. It only knows how to add or take away speed this way, right? So if I look at a projectile and I only look at the vertical component, oh, that makes sense. That's another chapter we had. But look at this number here. Look at that one. 5, 5, 5, 5, 5, 5. What's that? Let's see if Colleen knows. I know it's Monday morning, but why would the horizontal component stay the same? Yes, and Monday morning, excellent. Everybody see that? Because just because the ball is maybe being accelerated or decelerated up and down, doesn't it also have inertia going this way? Yes? Okay, and that doesn't change. Every year, I'll say, how many forces are acting on this ball after it leaves their hand? Every year I have people say 2. Tell me what they are. Well, gravity. You mean weight? Yeah, that one. Yeah. What's the other one? Inertia? That's not a force. What's inertia? A tendency. I know it's weird. But there's no force. Galileo has said, once an object's in motion, it doesn't take any force to keep it moving this way, does it? But the only force acting on a projectile, not counting air resistance, is gravity, isn't it? And that only acts in that direction. Okay. Anyway, so does this page make sense? Okay, let's flip it over. Now this one, you had to take a little time, and it talked about a scale. It said the scale was 1 centimeter is 5 meters. And how far does an object fall in free fall at the end of 1 second? Okay, if I forgot those numbers, I could do D equals 1/2 GT squared. Let's see, put 1 in here. 1/2 g is 5. 5 times 1 squared, 1. 5 meters. Okay, it's going to fall 5 meters, right? And it's going to fall that way. And then what about this? It's going to be 20, right? And then what? 45. Okay, so it's going to fall 5. It's going to fall 20 and 45. And what's this one? Is that 80? We had this in another chapter. We had this in another chapter. But what's the ball doing this way? Ooh. What's the ball doing horizontally? If the earth wasn't there, if the earth disappeared after I threw it, wouldn't the object go off at a constant speed horizontally? Yes? Well, I've had that too. That's called inertia. So ready, at the end of 1 second, you must be here horizontally. You must be here vertically. Okay, there I am. You must be here, and you must be, and I didn't have a ruler. You must be here, and you must be here. Ooh, and ooh. I get it. Did everybody get something like this?
Yes.
And that's where you get that, that's half a parabola, isn't it? That's where you get that idea that Galileo discovered that was a parabolic path. Okay, on that page? Okay, now the harder page, this is the one that, if you're not patient, if you're not detail-oriented, you probably mess this page up a little bit. Now, what if I don't throw it this way? What if I throw it this way? If the Earth disappeared, I'd still go off in a straight line at a constant speed. That's inertia, right? But the Earth is there, so I'm going to fall below that point by how much? How far below this point am I going to be after the end of 1 second? How many meters?
1 centimeter.
Wait a minute. You want to do it again? How many meters at the end of 1 second? How far does an object fall? 5 meters. At the end of 2 seconds, how much? Isn't that right? 20. So when you go over here, I should be right here at the end of 1 second. Well, you're not, because you're going to be how far below that point you're going to be? 5 meters? What's the scale? Oh, I need to go 1 centimeter down. So if you drew 1 centimeter, dot 1 centimeter down below, you did it. This is supposed to be 20 meters. That would be what? 4 centimeters? There we go. Everybody get that? How far is this one going to be? 45 or 9 centimeters, right? Okay. And the next one's supposed to be what? 16? We're going to do that. Now, did everybody draw something like that? Or did you just think it was still straight like the other one? I'm okay if you change it. But what do you think? So one of the questions the author asks, it says, estimate the number of seconds it remains in the air. How do you do that? How do you do that? Liam, I bet you know. Okay. Have a guess?
I guess 2.
How much?
2 seconds.
Okay, I'll tell you what. At the end of 1 second, it was here. At the end of 2 seconds, it was here. So it's going to be more than 2.
Yeah.
Go ahead.
I want to say 4, but I don't know.
Okay. At the end of 1 second, it was here. At the end of 2 seconds, it was here. At the end of 3 seconds, it was here. And
Oh. So less than 4, more than 3?
okay. Okay, so what do you think?
3.5. Could you use the distance formula to find the time?
I could. I'm not sure that today. Today, I'm going to actually show you how to get into the mathematics of this. But this page, he just wants you to estimate it, okay? But we're going to do all the details that you want. What did you come up with? Did you end up using equations?
No.
Oh. So I think most people use their scale drawing, and you think, well, that's 3 and that's 4. So what do you think? 3.3, 3.5? Is that what you came up with? And we are going to get into the details of that. And my favorite question is this one right here. Ooh, this is a good question. What do you think? Was he speeding or not? Yes.
I just have a question about the problem. Why would they want to know, like, what if he was speeding or not? If he just like veered off the thing and not?
Okay, that's a good question. Now, physics people sometimes come up with all kinds of things to, to just kind of make the question interesting. To me, if the guardrail was made out of paper or cardboard, I could tell you how fast he was going. But it's very difficult for me to tell you how fast he was going because it's probably made of concrete, maybe steel. He had to break through that. That would have slowed him down a little bit, right? But I think what they're trying to figure out is if that thing was made out of paper, how fast do you think he was going? And then figure out was he speeding or not. So let's try this. What happened here? Who can I ask? I don't know. Emma Shea, what do you think? See this thing? Do you think this number here meant anything? What do you think that number, hang on. What do you think that number meant?
That's the drop from the boost.
One more time.
That's the drop from the boost to the ground.
Right. And do you think that's just a random number they picked, or is there something special about that number?
I don't think it's random. I'm not sure.
And they could have put 5, but what is half of 9.8? So little g is really 9.8 meters per second squared, isn't it? So if I put that in the equation, even though we say the object's going to fall 5 meters, it's actually going to be 4.9. So watch this now. That was important. Because how long does it take an object to fall 4.9 meters? How long does it take, where's my distance here? How long does it take for an object to fall 4.9 meters? Well, 1/2 g is actually 4.9 meters per second squared. And if you want to solve for t here, what would that be? How long was that car in the air? How much? I don't think so. Let's try it again. 1/2 g is 4.9 meters per second squared, and the distance was 4.9 meters. So if I divide both sides by 4.9, what's 4.9 divided by 4.9? So, and the square root of 1 is 1, isn't it? So how long was that car in the air? 1 second. Okay, now, this is what I like about this question. I know the car was only in the air for 1 second, but how far would it travel this way if it was only in the air for 1 second? And what did it say?
24 meters per second.
Yes, he went 24 meters in 1 second. So how fast was he going? It looks like 24 meters per second, but I expected you to also write something about what do you think happened to his speed when he ran into the guardrail? So was he speeding or not? Definitely. There's no way you could run through that guardrail and not lose some of your speed, right? And so even after he ran into the guardrail, he still was going 24 meters per second. I guess that's what I like about the question. It made you think about, well, how am I supposed to know? How fast he was going? Well, he went 24 meters in 1 second. Okay, everybody okay on that? Okay, so whatever you want to finish up on that. Hey, you guys on the computers, does that have something to do with this class?
Yeah, we do.
If you guys on laptops, if that has nothing to do with physics, I'm going to close those up, okay? All right, go ahead, and if you'll put your name on here, whatever you want to finish, go ahead and finish it. And when you go back there, you put it on the homework stack, and then there are 2 pieces of paper and a ruler and a protractor, okay? So turn that in, get 2 pieces of paper, a ruler, and a protractor. All right. So turn your homework in and pick up one of each piece of paper, and then a ruler and a protractor. Now, it is true that the protractor is only for people that want to make it exactly. The models would look nice. If you want, I just drew a 50-degree angle. I estimated what 45 was. I added a little bit to it. I did that. All right. So now, today, the last lesson I want to show you is something you already have done. You've used trigonometry before. I'm going to use a little bit of trigonometry, not very much. And we're going to do something here, right? So it says here, a projectile is an object that moves through the air or space acted on only by gravity, or maybe there's some air resistance. Projectiles near the surface of the earth follow a curved path that are simple when horizontal and vertical components of motion are examined separately. And that's what Galileo was able to do. He said they were independent of each other. He studied them separately, and that's how he discovered this. All projectiles follow a parabolic path when being acted on by a horizontal and a vertical component before beginning, and then there's some equations for you, okay? So here's my first problem I want you to try. It says here a cannon fires a cannonball at 50-degree angle, and the speed of the cannon ball coming out is 80 meters per second. So let's draw a drawing showing what's going on here. Here's my, and you can draw a cannon if you want. That's a terrible cannon. Okay. Okay. So everybody okay on that? All right. Now, what the lesson you were supposed to learn from the homework is that every vector can be resolved into a vertical and horizontal component. Is that correct? So what we're going to do is, if you have your ruler, let's go ahead and make sure that line's like that. And here we go. Now, a physics person might do something that scares people, and they, I can't understand physics. They might say V sub x. What does that stand for? All they're doing is putting name tags on things. What do you think V sub x is? Uh-oh. Yes.
Velocity on the x-axis.
Right, the horizontal velocity. You see that? Okay, now, if I want you though, if I want to bring you in to the conversation, why don't we just call that x? Is it okay if you call that x? The x component? Okay. Now, the other component would be this one right here. And again, a physics person might say v in the y direction, or why don't we just call it y? And by the way, that's over here too, isn't it? Whatever that one is, that's over here. All right. Now, what I want to do is we want to figure out these two components. All right, so let's see how you do that. You want to do this one first? You want to do the y component? Everybody see that? I want to find out what is the velocity of the cannonball in a vertical direction. So ready? So in a vertical direction, all right, how do we do that? A little bit of trigonometry, okay? Here's a right triangle. What do you know about, as seen through the eyes of the 50-degree angle? Who are you? Who are you? Uh-oh, it's Monday, but we can do it. As seen through the eyes of the 50-degree angle, who are you?
Oh my gosh, it's opposite.
Opposite. And who is this? We have this one, don't we? I want to find that. I have that. What trig function uses opposite and hypotenuse? Wait a minute. We have to memorize those. So what is sine again?
Opposite over hypotenuse.
Opposite over hypotenuse, right? I thought I heard somebody say something else. And this is adjacent over hypotenuse, right? Okay, so ready. The sine of 50 degrees, and one more time, how did you know to use sine? Because I'm trying to find the opposite, and I have the hypotenuse, don't I? So the sine of 50 degrees equals the opposite y over what? Tell me you're actually following me. Tell me what goes right here, right? Ben, tell me what goes on the bottom here.
Be the y over hypotenuse, which would be.
Say it. How much? What's the size of hypotenuse? Yes. Yes. Everybody got that? Now we rearrange it, and so the sine of 50 degrees times 80 meters per second should give me the y component, shouldn't it? All right, can everybody put that in a calculator? And I worked out last night. I'm just going to double check to see if you got the same numbers I got. What is the speed of this cannonball in a vertical direction?
Oh, I got it.
Now you can check on the handout sheet. It actually has the number there. Do it on your own, and then check it on there, and I think you're going to find it. There it is.
Oh.
What did everybody get?
61.283.
Wait, what is it?
It was still a negative.
Yeah, I have mine.
Make sure you change it to degree.
Oh.
Yeah, yeah.
Switch it back to
Oh.
degree. Change your calculator
It's
back to
negative
degree.
20.
All right, wait a minute. Yeah. All right, what's the sine of 50? And then times 80? I think you should get around a little over 60. Are you getting a little over 60? If you're not getting if you're not getting something like 61, let's just round off to 61.3 for right now. So what does this means is that, what's the speed of the ball? I know the speed of the ball is 80 meters per second along its path, isn't it? Right now. But as soon as it comes out of the cannonball, it's doing two things. It's doing this, and it's doing that, isn't it? And so its speed in a vertical direction is pretty fast, about 61. Let's try the other one now. What if we want to find the horizontal component? Okay, look at your drawing. Look at your drawing. I'm going to try to find the horizontal component. And as seen through the eyes of the 50-degree angle, who is this guy here? As seen, what is it?
Adjacent.
Adjacent. So we're going to say cosine of what? 50 degrees. As seen through the eyes of the 50-degree angle, the cosine is the adjacent over the hypotenuse again. Oh, okay, rearrange. So cosine of 50 degrees times 80 meters per second. And that should give me the x component. What's the cannonball doing in a horizontal direction? All right, and again, I want you to do it without looking at the sheet, but the sheet does have the answer on there, so that confirms that you're going to get it right, hopefully. Now, if you don't get about 51.2, let me know, all right? What do you think? Yes.
51.4.
Oh, okay, 4? Okay, all right, I'm fine with that. Let's do that. I'm all right with that. All right, is everybody okay so far? Now, so far, he said, hey, this is not bad. This is not bad. Now, what can I do with this? What can I do with this information? This is where it gets to the next level, okay? This level here is not bad, isn't it, trig? A little bit of trig. Let's go to the next level. Look at the next question. It says, number 2, using this information, find the total time in flight. Whoa. How am I supposed to know how long that cannonball is going to be in the air? Any ideas? And I'll tell you, we're going to use an equation we used from another chapter. What do you think? What if, and here's what Galileo was able to do. He's able to see a projectile as this motion and that motion independent of each other. Can you tell me, what is this object doing that way? What's it doing? It starts out at what speed? It starts out at 80, right? 80 meters per second. What's happening to it as it goes up? It's going to slow down, isn't it? 70 meters per second, 60, 50. See that? So what equation could I use to figure out how long it takes for half of this trip? It's going to go up, and it's going to come down. So ready? The time for 1/2 of a trip is what? How would he do that? What equation has to do with free fall? So when it's at the top of the arc, isn't it going to fall? So can I find out how long it takes? If it starts at 0, and by the end it's going 80 meters per second, right? How long does that take? Let's try it. V equals gt. Remember this equation? Isn't that a free fall equation? You know, it's free fall had a little g in it, doesn't it? And this says if you want to find out how fast something's going, if it allowed to free fall for so many seconds, I can do it. Well, can we rearrange it? What can we rearrange it to solve for? Can we do that? Let's try it. All right, what is the, pretend that the cannonball's already up here and it's falling. It goes from 0 to 80 meters per second. And so what is its speed being allowed? It was allowed to pick up how much speed? 80 meters per second. And what's little g? And we should start using 9.8, but let's start using 9.8. Okay. I had someone in the other class ask, what kind of units would this have? What do you think would happen here? What do you think meters per second divided by meters per second squared? What do you think that would come out to be? Do you know?
Can you move it a little bit?
Okay, this way? Oh, okay. Anyway, what is meters per second divided by meters per second squared going to give you? Well, the math teacher would have done this. They would have said a fraction divided by a fraction is the same as a fraction times what? The reciprocal. And watch. Ba-deer, 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 ba-deer. Woo! Does it come out to be seconds? Okay, so what's 80 divided by 9.8? I know what it gives calculator. Ben, you got a calculator? What's 80 divided by 9.8? Are we getting something like a little over 6 seconds or not? Oh. How much is it? Oh, my fault. Darn it. Wait, I'm done. I made a bad mistake. Wait, bad mistake. I can't use 80. What's the matter with me? I just talked about, we're only looking at which component.
Oh, so it's the 61.
That's my fault. My fault. I got 2 wrapped up in the components. My fault. So I have to use the vertical component, and so it actually has a speed of vertically 61.3. And I apologize for that. I made that mistake. Okay. So what's 61.3 divided by 9.8? And did you get something a little over 6? Okay. So let's try that. Now, the person who did this, a book I got it of, they got 6.25 seconds. Is that what you got? Now, I got to be careful. Wait a minute. That's half of the trip, wasn't it? That's how long it would take to free fall and obtain that speed. So this is half of the trip. So what's the total time? What's the total time that this cannonball's in the air? What would that be? This is half the trip. What would it be? About 12.5 seconds? All right, what do you think about that? Okay, now, I want you to imagine this now. In the vertical world, we can use this equation here, V equals gt, and solve for t, and we can actually find out how long you were in the air for half of your trip. And then we multiply that by 2, and that's how long you were in the air total. What are we going to do now? We just investigated the vertical world. What's happening this way? What's the speed of the cannonball horizontally? It's right here, right? I want you to imagine this, right? You're going at 51.4 meters per second, and I'm going to allow you to do that for how long? 12.5 seconds. Well, how far downrange are you going to go? So what do you think? If you're going at 51.4 meters per second, and I allow you to do that for 12.5 seconds, what equation would you use? It's a simple equation. What equation would you use? What, you know the speed equation? So what is it? Distance equals speed times time. Is that right? One more time. If you go 60 miles an hour for 1 hour, won't that tell you you went 60 miles? Okay, so how far? The speed was 51.4 meters per second, and you're allowed to do that for 12.5 seconds. That's good. And so what do we get here? And I believe it's on the back here. There it is.
642.7.
What is the number?
642.75.
Whoops. Wait a minute. Oh, we're way down. Wait a minute. I think we're down to number 4. I think we're at question 4 here. Yeah. Did you get something like 640? Okay. So what I'm going to do is, here's another question I might ask. Let's see. What else would you know? Yeah. Okay, we got that. Oh, I know. Another question. How high did the projectile go? How do you do that? How do you know how high the projectile went? How do we do that? Alistair, you think you had this?
We do the vertical velocity over half the time.
Okay. So this right here is half. If we do half the trip, so d equals 1/2 gt squared, and so we're trying to find its height, right? 1/2 g is 4.9 meters per second squared. And we're trying to find, and do we have the time? What time are we going to use here? Because this is only the time for what? Half. So do I use the 12.5 or the 6.25? Okay, so let's put 6.25 seconds, and the equation says to square that, right? Put that in a calculator and see if you get the same answer as I did for number 3. How high did the projectile go? I worked this out last night, and I got the same answer that this book did. But did you guys get something about 191 meters? So you have to square the 6.25 seconds, right? And then times 4.9. So you get something like 191? Okay. So what I'm going to do, even though that's the lesson, you can't understand the lesson unless you practice it, right? So what I'm going to do is I'm going to let you you can either sit in groups of 2 or 3. I'd rather not do it by yourself, but if you just felt like you had to, you can. But the other sheet, what I'd like you to do is to find some partners and say, let's figure it out this side. And then tonight, if you have time to look at it, I'll give you 15 minutes tomorrow in class. But if you work on this a little bit tonight, and then tomorrow I'll give you 15 minutes, and you can ask me any question you want. And if I do have time to give a quiz, it'll be about a 15-minute quiz. It'll look something like this. The quiz will look something like this side right here, okay? All right, I'm gonna stop the video, and what I want you to do is find a partner, sit with them, and I'll be around. I'll help you as I walk around the room.